Good morning, students. In this lecture of quantum mechanics, we will discuss our next topic, that is spherical harmonics. So what are spherical harmonics? Actually, these are the functions, special functions, which are defined on the surface of the sphere, and we use these spherical harmonic functions in solving the partial differential equations. So suppose any periodic function which is defined on the surface of the circle, defined on the boundary of the circle, it can be expressed in terms of sum of sine function and cosine function. Any point which is defined on the boundary of the circle, it can be written as the sum of sine and cosine terms by using Fourier series. In the same way, in case of sphere, if any function which is defined on the surface of the sphere, it can be written as the sum of spherical harmonics. And spherical harmonic function or spherical harmonics, it is denoted by y L ml theta phi. Means this spherical harmonic function or spherical harmonics, it is a function of theta and phi, and its value, it depends upon the orbital quantum number and magnetic quantum number as well. So here, as we are studying the chapter Quantum Theory of Hydrogen Atom, and in this chapter we are discussing the electron in case of hydrogen atom. So we have derived three separate differential equations. One was the equation of radial wave function RR. Second, the equations containing theta wave function and phi wave function. And while looking at all the three differential equations, we can see that energy and potential, E and V, they don't appear in the equation of theta and phi. Phi and theta equations, they don't contain E and V, means they are independent of E and V. Only the equation of the radial wave function, RR equation, it contains energy E and potential V. It means when you will solve the differential equation of theta and phi, and you will find the solution of those two equations, you will find the solution of these two equations only once. Why? Because these equations, they don't depend upon energy and potential. Their solution will remain same for all the energies and potential. Only the solution of RR equation will change with the energy and potential. So for a spherically symmetric potential, suppose V is equal to VR, what you will do, because the theta and phi equations, they don't depend upon E and V, so they will not change with E and V by changing the value of E and V. It means what you will do, you will find the solutions of theta and phi equation only once. And then what you will do, you will take the product of these solutions. And the product of these solutions of theta and phi, that is represented by a spherical harmonic function. So what we will do, we will take a solution which is equal to the product of the solutions of theta and phi equation, means we will collect the two solutions and we will represent it by a single function, that is spherical harmonic function YLM theta phi. So actually this YLM theta phi is the product of the solution of phi equation and theta equation. We know that phi just depends upon magnetic quantum number and theta depends upon orbital as well as magnetic quantum number. So we know that what is the solution of phi equation? The solution of phi equation is this. We have already calculated in this chapter. And the solution of theta equation, it is this. Again, we have calculated this solution in one of the previous articles. So put the values of these solutions of theta and phi equations in this equation number 1. So when you will put these two values here, and here you have the product of these two constants. It will be one another constant, that is C. And we can calculate this constant by using normalization condition in this way. So this is all about spherical harmonic function. It is the product of the solution of theta and phi equation which don't contain E and V. So we solve the solution of these equations theta and phi only once.